Okay, so this theorem is going to formalize some of the things we saw in the previous example. So suppose you have a commutative ring, then an ideal P is prime if and only if, when you mod out by P, you get a domain. And we saw that actually a bunch. Let's just go back real quick. All right, so 9 was not prime. We did not get a domain. 11 was, the ideal generated by 11 was prime. We got a field, which is a domain. X squared, the ideal generated by x squared plus 1 was prime. We got C, which is a field, so it's a domain. This one we didn't write out, but we can do it real quick. Why not? So in R adjoin x mod x squared minus 1, what is going on here? X squared minus 1. We have elements. We have x bar minus 1 and we have x bar plus 1. And their product, they're non-zero, and their product is 0. So it's not a domain. We have 0 divisors. This guy, we also didn't do, but let's do it real quick. So if I take R adjoin x and I mod out by the ideal generated by x minus 2, we know by the problems I've been torturing you with that that is just R back, right? R adjoin x. When you set x equal to 2, you just get R back. That's a field, so in particular it's a domain. So this is the theorem in general, and one might ask, well, you got fields, why didn't you put field here? And that's because we were working with PIDs, and we'll see shortly that in a PID, that's what happens. In general, though, you are only promised a domain, and I'll give you an example of that in a second. All right, proof. Suppose, let's do the forward direction first. So suppose P is prime. And let's let A plus P, B plus P be an R mod P. We need to show that it's a domain. It's already commutative because it's a quotient of a commutative ring. We need to show that there's no 0 divisors. So let's take two elements in that quotient ring, and let's suppose that when we multiply them together, we get 0. Well, that's what we're supposing, so that the product is 0, but we can also do the product. The definition of the product is you multiply the coset representatives A and B. So what this is telling us is AB plus P is the same as P, or equivalently, AB is in the ideal P. But P is prime. And if we have a prime ideal and a product in it, A is in P or B is in P. But this says A plus P is 0 plus P, or B plus P is 0 plus P. So if we have a product of two guys being 0, it must be that one of them is equivalent to the 0 coset, which is 0 in the quotient. So R mod P is a domain. Okay, so that's the forward direction. If you're prime, then you're a domain. For the backwards direction, we're going to suppose that R mod P is a domain. This is actually an if and only if. We can read it backwards, but I'll do it in two separate directions. Suppose R mod P is a domain. We need to show that P is prime. Take A, B, and R such that the product is in P. We have to show that one of A or B is in P. Well, if we look at what happens in the quotient to the product A plus the corresponding coset represented by A and B, we get AB plus P, but AB is in P, so we're going to get the 0 coset. Let me just indicate it's the 0 coset. But R mod P is a domain. So the only possible way we can multiply two elements and get 0, what is 0 in that quotient ring, is if one of them was 0. So A plus P is P, or B plus P is P. Which is to say, in the first case, A is in P, and in the second case, B is in P. And that is what we wanted to show. We took a product in our ideal, and we wanted to show one of them was there, and we did. So, therefore, P is prime. I guess let's write that sentence out. Thus, P is prime. Okay, so prime ideals, when you quotient by a prime ideal, you get a domain. And if you quotient by an ideal and you get a domain, you must have been quotienting by a prime ideal. So prime ideals produce domains with the quotient process.